Okay, so 1.2, so now we're going to start looking at the arithmetic. So if you treat this as if you were treating your algebra rules and your third rules, okay, we will get these and they're very straightforward, okay. So on page 45 of your notes, okay, in the top of that I have included a table of rules there for you, okay, but like I said, if you apply your algebra and your third rules, that's how they all come out. Okay, so in the following definitions, we've got A, B, C, D, X, and Y. We have all those as real numbers. Okay, so remember, if we want to have that as a complex number, we need to include the I with that as well. Okay, but they will all be real parts to the number. Okay, so we've got the identities, the I equal to the square root of -1. So we imply that when we square both sides, so we have I squared is equal to -1. Alright, so we've got the inequality in there as well. So A plus BI is equal to C plus DI if and only if A equals C and B equals D. Okay, so the real part equals the real part and the imaginary part equals the imaginary part. Alright, so when we add complex numbers, we can only add the real part and we can add the imaginary part. Okay, so you treat I as a variable. Okay, you can only add or subtract like terms. Okay, so you have the real parts you need to add together, which is one term, type of term, and then you have your imaginary numbers, which is another part of the term. Alright, subtraction, same deal, so we can only do subtraction of the real part and a subtraction of the imaginary parts. Now, multiplication, so use your FOIL. However, if you do the last, thinking about the last term, so you got BI times DI. Okay, so it would be BDI squared, and then from the identity, I squared is -1. Okay, so whenever you have I squared, we will simplify that down to -1, or any powers of I, we can simplify again, so we don't have any powers of I. Alright, complex conjugate. Okay, so we have the real, the complex number, x plus yi. Okay, so the conjugate has a hat on top of it. Okay, and all you do is you change the sign between the real part and the imaginary part. Okay, so whenever you're referring to the conjugate, that is what you need to do. Whatever the sign is, you need to have the opposite sign between the real and the imaginary part. That means the real part's the same number, and the complex number is the same number, just different in magnitude, as in one's positive and one will be negative. And we use a complex conjugate for division. Okay, so when we do division, you know how we were rationalising the denominator of the third? We had to multiply by each conjugate. So we had the setup of the difference of two squares. Okay, so e.g., if we had 4 on 3 take away root 2, then we need to rationalise that denominator. Okay, so we need to multiply by the conjugate. Okay, so the conjugate is the same numbers with the opposite sign in between, and what that does is sets up the difference of two squares on the denominator, and that's what we need to be able to remove the third. Okay, it'll be equal to 4, 3 plus root 2, outside of 3 take away root 2, 3 plus root 2, so your only difference is the sign in the middle, so we square the first term, minus sign in between, and then we square the second term. So root 2 all squared is 2. Okay, same process with complex numbers, alright? So when we have complex numbers in there as well, we will rationalise, and because we have an imaginary part, but we will have I squared when we expand it out, and I squared is -1. Okay, so we will not have a imaginary part on the bottom of your fraction. Okay, so they're the rules for your arithmetic. Right, so let's look at some examples incorporating all that. Alright, examples. Simplify the following. I cubed. Okay, so we don't need to express any i's in relation to powers because we can simplify those with the identity. Alright? Alright, I squared times I, isn't it?
Yeah.
Alright, using your index laws, what's I squared? Yeah. Okay, so we can not have any powers associated with I at all. But if you have any powers, you need to do this sort of work. Okay, of course I to the power of 4 is going to be -1 times -1 if we break up our index laws, and then we'll have I to the power of 4 as 1. Okay, so we can always have powers of I as either plus or minus I or plus or minus 1. Okay, so that's what we need to keep in mind when you're doing this sort of work. Alright, addition 1 plus 2i plus 2 take away 4i. So we have two different numbers there. Okay, so we got complex number 1, complex number 2. Okay, so complex number 1 is 1 plus 2i, complex number 2 is 2 take away 4i, and we want to do an addition between those two complex numbers. Right, so just treat it like algebra. You can only add like terms. Okay, so I'm going to add the constant term, 1 plus 2, 3, 2i plus a -4i, so 2 take away 4, which is -2. So I've broken it down into my real and imaginary part when I'm adding two complex numbers together. Alright, a subtraction. Okay, so each of the brackets will represent a complex number. A complex number will have a real part and an imaginary part. Okay, so I guess all complex numbers have to have an imaginary part. They don't have to have a real part. Of course, we've said that we can let the real part equal 0. Alright, so again, so Z3 and Z4. So you're doing a subtraction between two complex numbers. You again treat it like your algebra rules, okay? So I and -3i are like terms, 3 and 2 are also like terms. So 3 take away 2, which is 1. I take away a -3i, so we have 1 take away a -3, 1 plus 3, and we have to put the letter involved with it. Okay, so it's nothing new, it's just incorporating our thinking with a new number system. Right, let's try multiplication. So 4 plus I, 1 minus 2i. Okay, so there's an infinite number of complex numbers because we can have an infinite number of real parts and also an infinite number of imaginary parts. Okay. So in that diagram I showed you, it was a bounded, okay, so really if you think about it, it probably wouldn't be so much bounded because there's an infinite number of numbers we can have of each of those number systems. Okay, but just to get that understanding that the infinite number of complex numbers. So we just do our FOIL. Okay, so 4 times 1, outer, 4 times negative 2i. Okay, so using your algebra rules, I plus 1, I times 1. Now I times negative 2i, so negative 2i squared. Okay, so what's I squared? Negative 1, so this becomes a negative 2 times negative 1. So 4, take away 7i, so we're doing the addition of the like terms here. Then negative 2 times negative 1 becomes a positive 2. Okay, be careful with that, don't write negative here, okay, because it's very easy to get the mistake. I squared is negative 1. Okay, so when you multiply those two complex numbers, we have another complex number with the real and the imaginary part associated with that. Any question? We understand this? Not so bad now? Not so scary anymore? Waiting? Waiting for the complex bit, are you? Alright, division of complex numbers. Alright, 2 plus I over 3 plus 2i. Okay, so you treat this as if you are rationalising the denominator. So you need to multiply by the conjugate. Okay, so the conjugate is the bottom part of that fraction with the opposite sign in between. We multiply by the conjugate because that will create a difference of 2 squares on the bottom, and we will get the denominator as a real number. Okay, what's your plus sign on the bottom? So the difference of 2 squares is a takeaway. However, when we do this times this, it's a negative 4i squared. I squared is negative 1, so it becomes a negative 4 times negative 1. Okay, so you need to be careful with those signs. Okay, so again we've got I squared here. Okay, negative 1, be careful with your signs. And we usually write it like that. Okay, so we're breaking up into the real and imaginary parts. Okay, and the reason why we write it like that instead of writing 8 take away I all over 13 is because the next question where it's asking us to identify the equality symbol there. So find the value of x and y if x plus y 3 plus 4i is equal to 2 take away 5i. Right, just a side note as well, complex numbers then is x plus yi. Some text you'll say a plus bi, Okay, same principle there. Now this really annoys me a little bit. Okay, a plus I, b. Okay, you will see in that as well. Okay, I like to leave the i's at the end. Okay, because you're treating it like a variable with the math that you're doing, and you don't have the variable before the actual number itself. Okay, so you will see that in your text and all that sort of stuff, possibly. Alright, but I've done all my notes, I've done it like this or this, kept the I at the end, okay? It's just so you know and you don't have any surprises in there, which is technically multiplying in any order you want, okay? But I don't like to see the I at the front, okay? That's just my thing. You can make it your thing if you want, or you're not going to be bothered by it. Anyway, so we need to find the value for x need to find the value of x, the real part, and y, the imaginary part. Okay, so what we're going to do is go FOIL this, okay, expand this right out. So 3x 4ix. So I'm treating the x and y as your main variables this time. Plus 3 y plus 4i squared. So this is really the left hand side. Okay, and then I'm seeing the I squared here, I need to tidy that up as well. So that will then become a real number and not left as an imaginary number. So 3x 4ix plus 3 iy take away 4y. Okay, so you've got to remember your signs. I squared -1. Okay, now I'm going to rewrite this is the real part and the imaginary part. So 3x take away 4y is the real part because they don't have i's with it. So that's the real part of your complex number. Plus 4x plus 3y, and factorise the I out, so the 4x plus 3y is your imaginary part. Alright, what do we do from here? Any ideas?
Minus y equals 4x plus 3y, and then 2 equals 3.
Good. Okay, so the real part here has to match the real part of this expression here. The imaginary part has to match the imaginary part up here. So 3x take away 4y is equal to 2, equation 1, and 4x plus 3y is equal to -5. Okay, of course we don't have to write i's there because we're just equating the real imaginary part in there. Okay, and now we have a simultaneous equation.
Oh boy.
Right, so I'm going to look at the elimination method. However, before I use the elimination method, because the coefficient of your like terms are not the same, so I'm going to have to manipulate them so that I get them the same. Alright, so if I aim to get the coefficients of your x, okay, to the same number, okay, so if I cross multiply, okay, or find the lowest common multiple, if I multiply everything here by 4, I'll get 12i here. And if I multiply everything by 3, this term here will also be, 12x, and this will also be 12x. Okay? So 12x take away 16y is equal to 8. Equation 3. 12x plus 9y equals -15. That's equation 4. Okay, so I've got the coefficient the same. I can then look at the elimination method. Same sign as well, 12x and 12x. So I need to do 3 take away 4. Or I can do 4 take away 3, or we can get the y's the same number, whatever you choose, as long as the maths works. Don't go off on a tangent anywhere. Be consistent what you've learnt in mathematics. And we'll get the same answer. Okay, switch the signs. So negative 25y. 8 take away a negative 15. So we've got 8 plus 15, which is 23. 16 take away 9, 8 take away 23. Yep. So y is going to be negative 23 on 25. Yeah, we can have fractions, okay, because they're still part of our real number system. Okay, so the imaginary part is negative 23 over 25. Right, so put that into one or the other equation to get the value for x now. 3x take away 4, lots of negative 23 over 25 equals 2. So 3x plus 82 over 25 equals 2. So 92. Okay, 3x equals 2 take away 92 on 25. So 50 on 25, take away 92. So we have 90, 42, negative 42 on 25. So x is going to be negative 42 on 75. There we go. Have them right. Okay, we're happy? Not entirely. Yep, alright, so the real part is, of course, the real part is x, the imaginary part is y. So if I hadn't set x and y, what I've just solved there, multiply them by 3 plus 4i, my answer will be, hopefully, unless I'm made an error, 2 take away 5i. Okay, so that's just sort of the algebra skills that you need for this section here as well. Alright. So now we come up to your first exercise in Fitzpatrick. 31A in there. We've got about 10 minutes. I think I've got enough time to do the next section as well.